In the last lecture, we have discussed on the static indeterminacy, how to find it for the various structures like the beam, truss, as well as the frames. And in this class, it's a continuation of the previous one, we'll be learning some more important definitions for our problem solutions. First one is action and displacement equations. So the spring displacement D, please note that we were referring the D as displacement and the A as action, and always for the spring the D, which is displacement, is equal to the F into A, where F is the flexibility matrix, or actually the D is proportional to A. As the force is increasing, displacement is increasing, and D is equal to F into A will be the equation. And the A, which is the action, is equal to S into D. So there is a relation between F and S. One is the inverse of other. The stiffness S is equal to 1 by F, which is equal to F inverse, and the flexibility matrix of flexibility F is equal to 1 by S is equal to S inverse. So both the stiffness and the flexibility are the inverse of each other, and the above equations can be applied to any linearly elastic structure. We will see some problems to make the concept clear. So we were asked to write the flexibility and the stiffness of a beam subjected to a single load. So the beam is simply supported with hinge at one end and the roller at the other end. It is acted by an central concentrated action or the force A, and definitely there will be a displacement D, and it will be maximum at the midspan. The beam is of length L, and the load is actually exactly center, so L by 2, L by 2. So you know the maximum displacement of this beam subjected to a force P. So the displacement value will be P L cube by 48A. Okay, P L cube by 48A. So the flexibility F is equal to, it is the deflection caused by an unit load. So instead of P we will write 1. So PL cube by 48 is equal to, taking P is equal to 1, it will be L cube by 48A. So we know that the stiffness is just 1 by F. So stiffness S is equal to 48 EI by L. Okay, and actually the A is actually the loading diagram. The exact load is there, the deflection is there. The B is the representation of the flexibility calculation, and the C is the representation of the stiffness calculation. In the flexibility calculation, you should apply an unit load, and the corresponding displacement is called as the flexibility. And in the case of stiffness, you are supposed to apply an unit displacement. That is, the displacement should be 1, and the force required to cause unit displacement is taken as a stiffness. So please keep this in mind very clearly for finding the flexibility method, finding the flexibility matrix. You are supposed to make the load unit, or you are supposed to apply unit load and then measure the deflection at the various points. To find the stiffness matrix, you are supposed to keep the deflection or rotation, whatever. Deflection is a general term, so deflection at various point to be unit value, and the corresponding forces will be the stiffness value. Some more examples. flexibility coefficient of a beam subjected to several loads. So in this case, there is A1, there is A2 and A3. A1 is a downward load, A2 upward, and A3 is a moment. It's actually a continuous beam, one unhinged roller, and due to the action of all these load, there will be D1 deformation here, D1, then D2 will be there. As moment is clockwise, there will be an as a moment is clockwise, there will be an upward lifting of the beam, which will make an upward curve and it's a downward curve. And definitely the D1 is influenced by A1, A2 and A3. D2 is influenced by similarly A1, A2, A3, and D3 is also influenced by A1, A2 and A3. So these are the first figure represents the various actions on the beam A1, A2, A3, and deformations are noted in the second figure. Okay. Next one is to find the flexibility matrix. So to find the flexibility matrix, as we discussed, you should apply the unit load at each point separately. Okay, so for the first case, the A1 should be replaced by 1, and then you should represent the displacements accordingly. So when you apply an unit load in the place of 1, F11 will be the flexibility matrix, which is the displacement at the point 1 due to the force applied at 1. F21 is the displacement at point 2 due to the force at first position. F31 is the displacement at 3 due to the force at the first position. Similarly, apply the one load. So the A2 was upwards, so you should apply the unit load in the same direction. And also the flexibility matrix F12 will be the displacement at the first position due to the second load. F22 will be the displacement at the second position due to the second load. F32 third position, second load. Similarly, you should write for the action 3 also. You should apply a unit moment in this case, as the action is a moment. So D1 is the total deflection. D1 is equal to this one, like D1 plus D2 plus D3, that is so D1 is equal to D11 plus D12 plus D13, which represents the deflection at the first position due to the various load 1, 2 and 3, and D2 is equal to, so the first one will be same, D2, and the second one was the effect, like where the force is applied, first position, second position, third position, so D3 also there. So D1 is equal to, we know D11 is equal to, D is equal to F into A. Hence D1 is equal to this equation, D11, that is F11 into A1 plus F12 into A2 plus F13 into A3. Similarly D2 and D3. So in this equation, the F11, F12 and F13 are the flexibility coefficient. So it is defined as flexibility coefficient F12 is the displacement at the first position, or the displacement corresponding to A1 caused by an unit value of the A2. Okay, so this one is coming in the first place here, 2 in the second place. In general, the flexibility coefficient Fij is the displacement corresponding to Ai caused by an unit value of Aj. Let's see for the stiffness coefficient also. So we learned how to frame the flexibility coefficient. Note that you should apply the unit load at various points separately and write the equation to get the flexibility coefficient. And the next one is to find the stiffness coefficient of a beam subjected to several load. So we have discussed previously that to find the stiffness, you should give unit displacement. It can be unit vertical displacement, it can be unit rotation, and the corresponding load will be the load has to be find out. So to find the stiffness coefficient, once again you please note that for the previous one you applied when you applied the A1, the A2 and A3 was removed, right? And for the second load, when you apply unit load, the A1 and A3 was removed, and so for each step the only the acting load is taken into consideration and all the other loads are removed. Okay, to combine it and to get the flexibility matrix. In the case of stiffness coefficient, so these are the actions on the beam. Let's previous same problem A1, A2, A3, and these are the general deformations corresponding to action D1, D2, D3. Okay, to find the individual stiffness coefficients, stiffness matrix, you should apply unit displacement at various action points. So in the this is actually case 1, this is case 2, and this is case 3. So when you deal with the case 1, you should give the unit displacement at the position 1, and the second one was actually D1 is a vertical displacement, D2 is vertical displacement, D3 is rotation, right? So when you give unit displacement at the first position, please note that the displacement at the second position and the rotation at the third position should be 0, because we are focused or we are giving only unit displacement for the first action point. That's why we are providing a roller here, so that there is no displacement vertically here. We are providing a fixed one, so there is no rotation here. So this will give you the S11, S221 and S31. Okay, similarly for the second case, when you should apply the displacement in the upward direction for one value, and this should be actually 0, and this also should be 0. So only one is applied, and the corresponding stiffness coefficient are stiffness coefficient at the first position due to the second position displacement, and S22 and S33. In the third case, you should give a rotation for the at the third point, and all other, that is here and here, there should not be any vertical displacement. So this will be the case, and these are the corresponding stiffness coefficient. So unit displacement applied corresponding to each degree of freedom separately, keeping all other displacements 0. So like the previous one, A1, this action A1 is equal to A11 plus A2, A12 plus A13. So we know from the equation that A is equal to SD, A1 is equal to S11 D1. That is, we are replacing these terms. Okay, so A2 is equal to S21 D1 plus S22 D2 plus S23 D3. Similarly A3 also, where the S11, S12 and S13 are the stiffness coefficient. The stiffness coefficient S12 is defined as the action, that is a force corresponding to D1 due to the unit value displacement at D2. In general, the stiffness coefficient Sij is the action corresponding to Di caused by an unit value of Dj. We have some more problems. We'll quickly see these problems. Example 4, the flexibility and stiffness coefficient of a beam. So it is actually an overhang beam with a tip and A1 vertical load and a moment A2. These are the actions. And to find the flexibility coefficient, you should note that you should first apply A1 is equal to 1 individually or alone, and then you should remove that time A2. So for second stage you should apply a unit moment and should remove the vertical load. So this is actually the first case and second case. In the first case you are applying a vertical load and the corresponding flexibility coefficient F11 and F21. These are the displacements, right, are noted. And for second case we applied an unit moment and then the corresponding flexibility coefficient or displacements are the F22 and F12. To find the stiffness coefficient, if you remember, you should apply the vertical displacement of 1 and also the rotation should be 0. So this condition is possible for the sinking supports like this, that is the rotation is actually 0 and there is a deflection is equal to 1. Okay, and for the second case you should arrest the vertical deflection. You should give only an unit rotation which will be look like this. So there is no vertical movement, there will be only unit rotation. This unit displacement 1 and the corresponding forces actions are known as the stiffness coefficients S11, S21, S12 and S22. This is a very base concept for finding the flexibility and the stiffness coefficient. To find the flexibility and the stiffness coefficient of a truss, here a truss is supported by a hinge as well as a roller. Two actions A1, A2. So to find the flexibility coefficient, you know very clearly now that you should remove the A2. In the direction of A1, apply an unit force, right, and the corresponding displacements are written as F11, F21 for the first case, and instead of unit load in the A2 direction we have F22 and F12. We are showing that the unit load in direction of A1 and also in the direction of A2 1. So these are the flexibility coefficients. For the stiffness coefficient, you know that actually both are axial, so both are actually displacement, horizontal and vertical displacement. For finding the first stiffness coefficient, you should apply an unit displacement in direction A1 and you should restrict the movement upwards, right? And for second case you should restrict the horizontal movement and you should allow an upward movement for a unit displacement, which are shown in the figures as D and E. Here the unit moment displacement in the horizontal is permitted, or it's moved, and it is obstructed. There is no vertical movement. In the second case there is a vertical movement, unit vertical movement 1. Here it was also 1 unit movement in the horizontal direction, and there is no horizontal displacement. So in general, the flexibility matrix in general, D1 is equal to, if we have numerous actions, it is D1 is equal to F11 A1 plus F12 A2 up to F1 n AN for n number of actions. Similarly, D also can be n displacement due to n actions. If we write this in the matrix form, and this is the basis of the flexibility matrix. So it is a flexibility matrix is this matrix which connect the displacements and the action. So from this simple equation d is equal to f into a, we have developed this into a matrix. D matrix is equal to f matrix into a matrix. Similarly, we have a matrix is equal to s matrix into d matrix. Yeah, this is a matrix form. D is equal to fa, d is equal to f into a. D is the displacement matrix, f is the flexibility matrix, and a is the action matrix. And Fij are the components in the matrix are the flexibility coefficient. Okay, so this is actually the flexibility at the I. Flexibility is always displacement at the ith position due to the action at the jth position. The similar definitions and derivations for the stiffness matrix, it is actually connecting the action and the displacement. So please note that in the flexibility matrix you will find the you will connect the displacement with the action by the flexibility matrix, and in the case of stiffness matrix you will relate the action with the displacement. So here actually you are applying unit displacement in the case of stiffness matrix, and you will get the corresponding a1, a2, a3. And if the value of the d1 is changing, that is for the unit value for d1, d3, the a1, a2, an is equal to this matrix. When the values increasing, the displacements are more than the unit value, correspondingly the actions also will change. Similarly, the matrix for the action a1, a2, a3, etc. for the unit value d is equal to f, and as the value of the action force is increasing, correspondingly the displacement matrix also the values will be increasing. So A is equal to S into D. A is the action matrix vector, S is the stiffness matrix, and D is the displacement matrix. S, I, J are the stiffness coefficient. So the relation between the flexibility and stiffness matrix, A action is equal to stiffness matrix into D matrix, and is equal to S into F into A, because we know D is equal to F into A. And the flexibility matrix is always the inverse of the stiffness matrix. Some more problem, and now we are going to physically solve some structures for a cantilever element. So it will be a fixer at one end, free at other end. Applying P and M, there will be a deflection vertically delta, rotation theta, and the length L for the beam. E and I are the elastic modulus and the moment of inertia respectively. So you know delta is actually resulting from both the action of P and M. Delta is equal to PLQ by 3A. It is the deflection of a cantilever beam with the tip and load P, PLQ by 3A, plus this is the deflection of the cantilever at the tip due to the application of a moment ml square by E. It's total delta. Theta is equal to PL square by 2EI plus ML by EI. So for knowing these values, you should learn the PDFs I have shared with you, the basic static equations or the solutions for the displacements and the slopes for different loading conditions, which you have studied in the previous classes. So combining delta theta is equal to LQ by 3EI, this one, then L square by 2EI here. Here also P is there, M is there. So delta theta are the D, right? They are the displacement, and this is actually the A. So D is equal to F into A. This is the flexibility matrix. And please note that always the flexibility matrix will be a symmetric matrix. That is, always 1 2 will be equal to 2 1, and definitely 1 1 and 2 2 will be a different value. So this will be a cross check for you for the upcoming problems. So this is actually a physical approach. We are directly writing the values and getting the relationship. Then how to write this one in terms of flexibility coefficient, that is, we'll be applying the unit forces at each position separately, and we'll write the flexibility coefficient and we'll club it. So if you don't know the values of the deflections by heart, you can also solve by the actually but you can't actually directly solve because you need to know the value. But this is actually a different approach where you can cross check it. Yeah. So in the case of flexibility coefficient, for the first case you are applying a unit law A1, and you are removing the A cube first case. So F11 is equal to L cube by EA, because previously it was P L cube by E 3EI. The P is equal to 1 now, and F21 is equal to F12 is equal to L square by 2A. It was M L square by 2EA, but M is equal to 1 now, and for F22, due to the action of the moment, it is actually ML by EI. M is equal to 1 now. So D1 is equal to F11 A1 plus F12 A2. D2 is equal to F21 A1 plus F22 A2. And we'll get the same flexibility matrix as the previous one. And but the actually instead of D we got delta and theta for the previous one, and for the action the real actions were written in the previous matrix, but here it is creating the D, F and A. Okay, whatever the flexibility coefficient will be same, and always it will be symmetric. This value will be equal to this value, and this value will be never equal. Okay, so we are finding the stiffness coefficient. So one thing to note is that always stiffness coefficient, this value will be an inverse of this F. So F inverse is equal to S if you want to cross check it. Yeah, so to find the stiffness coefficient, there are actually two actions, right? One a vertical reaction and one is a moment. So it will be delta and theta are the T variables. So in the first case, delta, there is a vertical displacement should be unit displacement should be given, arresting the rotation. And the second case, to find the stiffness coefficients, you should give an unit rotation and you should arrest the vertical displacement. So these are done as a case D and E. In the case of D, the vertical displacement of 1 is given, arresting the rotation. So there is no rotation here, only there is unit displacement, and the corresponding the forces are S1 is equal to 1 is equal to 12A by L cube, S21, S12 is equal to minus 6CA by L square, which you have studied in your previous classes. S22 is equal to 4A by L, and so combining A is equal to SD, writing S11 here, S12 here, S21 here, and S22 here. you'll get the stiffness coefficient relating the A action and displacement. So F inverse is equal to S inverse is equal to I. It will be a matrix. So the flexibility matrix and stiffness matrix are relating actions and corresponding displacement. Flexibility matrix F is obtained for a structure analyzed by flexibility method, that is applying the unit loads at various points. It will be the inverse of the stiffness matrix X obtained for the same structure analyzed by the stiffness method. It will happen only if the same sets of action and the corresponding displacements are utilized in the two methods, because in both the method stiffness and flexibility we are taking the like a1 a2 a3 are the currently we are taking the three actions and the displacements at that point itself. Then only we can compare the stiffness and the flexibility coefficient. If you have idealized to a different point, then the this correlations won't work. So that's all for today.